Hello everybody, now we are going to solve a problem from enhancement MOSFET, E MOSFET. The question is to determine the Q point, Zi, Z0 and AV for the circuit given. So this is the circuit given in which voltage divider biasing is applied. So these two resistors 10 mega ohm and 45 mega ohm are responsible for this voltage divider biasing. As a first step, let's determine the Q point. So to find the Q point, we should do the DC analysis. So for that, we should have the DC equivalent circuit. So how do you get the DC equivalent circuit for that case? Here we have the capacitors C1, this one is C2. These are all the coupling capacitors. As well as we have this bypass capacitor C3. So these three capacitors will be acting as open circuit for DC so that we can remove these particular portions and we'll get the circuit like this. So this is the DC equivalent circuit after removing the capacitors. So from this circuit we are going to determine the Q point. So with the help of graphical analysis we are going to determine the Q point. So in the graphical analysis we are going to plot the transfer characteristics curve for the E MOSFET. So this transfer characteristics curve is drawn with VGS versus ID. So this VGS is the gate to source voltage and this ID is the drain current. And for this enhancement type MOSFET, VGS is positive only. In order to plot this VGS versus ID, we have to first identify some points so that we can draw the graph. In this, the step one is to find out the coordinate points from the given data. So what are all given here? If you look at this, here the VTH is given as 1 volts. What is VTH? VTH is the threshold voltage. So after this threshold voltage only the current starts flowing. That is the ID current starts flowing. So from the threshold voltage we can identify one coordinate point. So up to this threshold voltage the current is 0. So we mark the point as 1 volt comma 0 milliamps. That corresponds to this threshold voltage as 1 volt and 0 milliamps as ID current. So we got the first point. Now from this we are going to find out the second point. So it is given as ID equal to 8 milliamps at VGS is equal to 3 volts. So this is our second point with the given VGS voltage as 3 volts comma the corresponding ID current as 8 milliamps. Now we move on to step 2. In step 2 we are going to find the points from the current equation. So what's the current equation? ID equal to K into VGS minus VTH the whole square, in which we can use this VGS value, VTH value and ID value given in the specification to find out this K. K is a constant that depends on the device parameters. Now substituting the values for ID, VGS and VTH given in the problem itself, in the specification itself, we can find out this K parameter. So that is equal to 8 into 10 power minus 3 as it is 8 milliamps ID current divided by 3 minus 1 the whole square, where 3 is VGS and VTH is 1 volt. It is 2 square. So now we get the K value as 2 into 10 power minus 3 A by V square. This is the unit A by V square. Amperes per whole square. After finding this K as 2 into 10 power minus 3 amperes per whole square, we are going to find out the points from this current equation. So this is coming at a second step. In this, we substitute the value for this K first. So it is 2 into 10 power minus 3 into VGS minus VTH the whole square. So for finding the K value only, we have substituted the ID value as well as the VGS value as 8 milliamps and 3 volts, which is also known as ID on and VGS on. But for finding out this coordinate points to draw the transfer curve, the ID and the VGS values are not known to us. Only the VTH is known. So, so on that case, we substitute this VTH values only. After that, we are going to assume VGS value and then find out this ID value. So assume VGS is equal to 2 volts. Now substitute this value into this current equation. So we get this as 2 into 10 power minus 3 multiplied by 2 minus 1 the whole square. we get the ID current as 2 into 10 power minus 3 amperes. So ID equal to 2 milliamps. So now we got the third point using this current equation. Similarly, we proceed with one more point, assuming this VGS as 4 volts in order to get the fourth point. So when you substitute this VGS is equal to 4 volts, then the ID current becomes 2 into 10 power minus 3 multiplied by 4 minus 1 the whole square. So that we get this as ID equal to 2 into 10 power minus 3 into 3 square. 3 square is 9. So 9 into 2, that is 18 milliamps. So the fourth point is, so we got the fourth point. Now we'll plot all these 4 points. Before that, let's summarize these 4 points. So the first point is 1 comma 0, which we got from this VTH comma 0 ID current. Then the second point we have written using the given spec, that is VGS on and ID on, that is 3 volts VGS on and ID on is 8 milliamps. Then we got the third point using the current equation, so it is 2 comma 2. Then we got the fourth point also from the current equation, which is 4 comma 18. Now we plot all these 4 points in the transfer characteristics curve drawn for VGS versus ID. Along the x-axis we have VGS and along the y-axis we have this ID current. So first we plot the first point 1 comma 0. Then the second point is 3 comma 8. So here we have this 3 and here we have this 8. So we have plotted the second point also. What is the third point? Third point is 2 comma 2. What is the fourth point? Fourth point is 4 comma 18. This is 4 comma 18. Now we can join these points to plot the curve. So initially it is without any current flow up to this VTH. So now we'll join the points like this. Here it is. After plotting this graph, we need to find out the DC bias line. So how to do that? So this is step number 3. So step 3 is to draw the DC bias line or load line. To draw this DC bias line or load line, we are using the DC equivalent circuit. So in this equivalent circuit, this point is G, that is the gate point. And we know that the current entering into this gate terminal is equal to 0. That is IG current is equal to 0. And we can write the input side KVL equation as VGS is equal to VG minus VS. Okay, to find out this VG, we are using this voltage divider rule. So what it is VG equal to VDD into R2 divided by R1 plus R2. So substituting the values VDD, R2, R1 and R2. So this is your VDD and this is your R1 and this is your R2. 25 volts, 10 mega ohms divided by is 55 mega ohm. So it is 250 divided by 55. So the answer is 4.545 volts. Substituting this VG into this input side KVL equation as 4.545. So we got this as VGS is equal to 4.545 volts minus VS. In this, what is VS? So this is RS. RS is the source resistance. And through this source resistance, the current ID is flowing. So at the source point, the current ID is flowing so that this VS potential can be written as ID RS. So if you substitute this expression into this VS, we get VGS as 4.545 minus this ID RS. The source resistance is given in the problem as 0.8 kilo ohm, so that we can substitute it into this KVL equation. Again, in this KVL equation, which is used for biasing, we have two unknown values, that is ID as well as this VGS. So what's the purpose of this input side KVL equation? It is to find the DC bias line. So we need to find out these two things. VGS is equal to what when ID equal to 0, and we need to find out ID current when VGS is equal to 0. So in place of this ID, if I put this as 0, then this equation becomes VGS is equal to 4.545 volts. So now we got the bias point 1 with 4.545 volts, comma 0 milliamps. Now we are going to get the bias point 2. For that case, we have to substitute this VGS equal to 0 in this equation, KVL equation, and find out this ID value. So when we substitute VGS as 0, when you solve this, we get the ID value as 4.545 divided by 0.8 into 10 power 3. ID equal to 5.681 milliamps. 0, 5.681 is the bias point 2. So now we are going to mark bias point 1 and bias point 2. So we are going to mark this point at 4.545 here. And then we are going to mark 0, comma 5.681. It is coming around here. So now we can join these 2 points to draw the DC load line. So we are going to mark this intersection point as Q point. So we have this Q point where we have this VGSQ as 2.25 volts and IDQ as 3 milliamps. So now we can mark them. This is VGSQ. Then here we have this IDQ. So we have got the Q point now. So we have done the DC analysis, and in that we have determined the Q point as 2.25, 3. That means VGSQ equal to 2.25 volts and IDQ is equal to 3 milliamps. Now in order to find out this ZI, Z0 and AV, we are going to do the AC analysis. So to perform AC analysis, we are doing some preliminary work like this capacitor is not named, we name it as C1. Similarly here at the output side we name this as C2, and across this resistor, which is the source resistance, we have a capacitor that we name it as CS. Okay, and this point is our gate point, and this point is drain, and this point is source. And this capacitor C1 is the coupling capacitor, C2 is also the coupling capacitor, and CS is the bypass capacitor. And during AC analysis, these capacitors will be acting as a short circuit, so that we can replace all these three capacitors with the short circuit like this. So here we do this modification, and here also we do this modification, second place, and in the third place we do this. Because of this short circuit, what happens to this RS, it will act as a, this would become an open circuit. So this is your fourth place where you need the modification because of this AC equivalent circuit. And this 25 volt is our VDD, that is supply voltage, and this supply voltage or the DC voltage will be replaced by a ground. So here we do the modification. So these 5 points need modification so that we'll get this circuit like this. So this 4 and the third together give you the short circuit line. Okay, so you will be getting this modification again like this. And here you see this is your gate point, right? And one arm of this 45 mega ohm is connected here, the other end is grounded. So this particular portion can be actually redrawn something like this. Okay, so here you will be getting this 45 mega ohm instead of this. So that we have done here like this. Okay, so this is your R1, this is your R2, and this source point is directly grounded, and this RD is, one end is connected to drain, the other end is connected to the ground. Okay, so we have the equivalent circuit after short circuiting the capacitor as well as grounding the VDD and open circuit that RS resistance. Now we are going to have the small signal model for this. So the green box within which we have this components, right, that represents our small signal equivalent model for this E MOSFET. So this is our G, that is the gate point, and this is the source point which is directly grounded, and this is our drain point. Okay, and this gate to ground is actually open because it is of very high input impedance. And then on the output side we have this dependent current source. Okay, so that is given here like it, like this. So that is given as GMVGS, isn't it? So this dependent current source depends on this VGS value as well as this transconductance parameter GM, and that is connected in parallel with small RD, and then connected in parallel with this capital RD. On the input side we have this R1 resistance and R2 resistances are connected in parallel. Then we have this input voltage VI and this input impedance Zi when looking into the circuit. Similarly, at this side we have this V naught and Z naught as the output impedance when we are looking into the circuit from outside or output side. So now we are going to determine this Zi. So we can easily calculate this Zi. So when you are looking into the circuit, then we have only two resistances R1 and R2. They are connected in parallel. So that we can calculate it as R1 is 45 mega ohm. Since it is the parallel connection, we have to multiply it by this R2 value, that is 10 mega ohm, divided by R1 plus R2. So it is 45 plus 10 mega ohms. So these two get cancelled, so that here we are getting 450 into 10 power 6 divided by 55. So this value is equal to 8.18 mega ohms. So we got the Zi parameter. Then we are going to calculate this Z naught. Z naught is equal to actually the parallel combination of small rd and the capital RD. The small rd value is not given. Sometimes it would be given using this GOS or HOS. If HOS or GOS are mentioned, then we can calculate this RD as 1 by GOS. If HOS is given, then also there we can calculate it as 1 by HOS. But these parameters are not given. Another thing is usually this RD value is very much greater than this capital RD, so that it can be neglected as we have the parallel combination of these two, so that this Z naught would be equal to capital RD. So in our case this capital RD is 2 kilo ohm, so we can write it as 2 kilo ohm. So we got the answer for Z naught also. Then the third parameter which is to be determined is AV. AV is equal to minus GM into capital RD. This is the approximation, okay. So in this RD value is known to us, it is 2 kilo ohm, but this GM parameter, what is GM? GM is transconductance. So that value is not known to us directly, but we can calculate it. So that can be calculated from this ID current. The equation for current ID is equal to K times this VGS minus VTH the whole square. So this GM parameter is nothing but the differentiation of this ID current with respect to VGS. So that is equal to 2K VGS minus this VTH. In this VGS is at the Q, that is VGS Q values should be substituted here. And here we know this K values, that K value is the device parameter and it's a constant and we have already calculated it. So this GM can be calculated as 2 into this K parameter value is how much it is? It is 2 into 10 power minus 3 amperes per volt square, isn't it? So that is multiplied by this VGSQ. VGSQ also calculated by us as 2.25 volts minus VTH is given in the problem as 1 ohm. So this is equal to 4 into 10 power minus 3 multiplied by 1.25. So this value is equal to 9 into 10 power minus 3 Siemens. So GM is equal to 9 millisiemens. So this is the answer for this GM. Now you can calculate this AV. So this AV is equal to minus GM into RT, isn't it? So that is equal to minus 9 into 10 power minus 3, that is millisiemens, right? Multiplied by RD is 2 kilo ohm. So it is 2 into 10 power 3. So these two get cancelled. So it is equal to minus 18. So AV is equal to minus 80. So now we can summarize the answers as Q point is equal to 2.25 volts, 3 milliamps, and Zi is equal to 8.18 mega ohms. Zi is equal to 8.18 mega ohms, and Z naught is equal to 2 kilo ohms, and AV is equal to minus 18. Okay, I hope you have understood this problem. Thank you.